A probabilistic model is a mathematical description of an uncertain situation. This is the overall concept, but I find that often people have a hard time trying to understand probabilistic models due to terminology, because we have a lot of terms like experiment, outcome, event, sample space, probability law, and if you don't really understand what each of these mean, you will struggle trying to understand examples and how a probabilistic model really works. So first of all, let's try to get the terminology straight. Probabilistic models are built upon a fundamental framework, and the elements of this framework is what we have to understand first. When we assess a probability, something is happening, right? There is an underlying process that will produce one and only outcome. This process is what we call the experiment. For example, you toss a fair coin. Whenever you toss a fair coin, exactly one outcome is produced. It can be heads or it can be tails. Now, the set of all possible outcomes is called the sample space. In this case, the sample space set has elements heads and tails. These are all the possible outcomes. We usually denote the sample space by the letter omega. Now, what is an event? And this is where I often see there is confusion. An event is a set of outcomes, and it is any subset of the sample space. So when you say that an event occurs, it just means that the single outcome of the experiment happens to fall inside that set. Remember, we are still talking about a single outcome for the experiment. Whenever you toss a coin, you will only get heads or you will only get tails. But the event may be a set with more than one element. So in our example, we can have a subset with only tails, a subset with only heads, a subset with heads and tails, and we can also have an empty set. Let's write that down. So possible events. First, the subset with heads, which means the event coin lands heads. Then the subset with tails, which means coin lands tails. Then the subset with both elements, which is h, t, and which means coin lands either heads or tails. And finally, the empty set, which means coin lands neither heads or tails. This may sound a little counterintuitive, right? You may be saying, what do you mean neither heads or tails? Of course, it will always land either heads or tails. And that's perfectly fine. We're talking about probabilities here. So later we will see that the probability of this event happening is 0. It will never happen. On the other hand, what is the probability that the coin will land heads or tails? This will always happen, right? Remember, this subset corresponds to the whole sample space, which means this event is always true. Let's say you toss the coin and you get the outcome heads. That single outcome belongs to the first event and it also belongs to the third event. So we say that both these events occurred. It does not belong to this event, so it did not occur. Let's see a bigger example. Now our experiment is toss 2 dice. An important point here is that there is no restriction on what constitutes an experiment. So an experiment could be a single toss of a coin, as we said earlier, but it could also be 2 or 3 or 10 tosses or an infinite sequence of tosses. Here our experiment is the toss of 2 dice. Now, what is the sample space of this experiment? If it were only one toss, the sample space would have 6 outcomes, right? 1 to 6. But since our experiment constitutes 2 tosses, we have to work with pairs. And we will actually have 36 pairs. For example, we have pair 1 and 1. So the first number in this ordered pair is the first toss. the second number is the second toss, we could have 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Then you would have 2, 1, 2, 2, etc. I'm not going to write every single one of them, but you get the point. So we have 36 pairs. We can call them ij. Now consider the event. The sum is 7. What are the possible outcomes that fall into this event? Well, this event is the subset of pairs where I plus j equals 7. So it is the set of pairs 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Now let's say the experiment produced the outcome 2 and 5. Since 2, 5 is in the event set, we can say that the event, the sum is 7, occurred. So I hope it is now clear what are an experiment, the sample space, a single outcome, and an event. Next, let's talk about the probability law. The probability law is a rule that assigns a number to an event and specifies the likelihood of that event, meaning of that set of possible outcomes. Let's call this event A. Then P of A, which is the probability of A, is a number that tells us the likelihood of A happening. So of this set of possible outcomes happening. So within this experiment, if someone asks you what is the likelihood that the sum is 7, P of A is the number that will tell you this, the likelihood of this event happening. The probability law must follow 3 axioms. First one, nonnegativity. P of A is always greater or equal to 0. Second, additivity. If A and B are disjoint events, then the probability of A union B equals the probability of A plus the probability of B. And finally, normalization, which tells us that the probability of the entire sample space is 1. We can write this as the probability of omega, which is the entire sample space, equals 1. On the other hand, the probability of the empty event is 0. So this implies that the probability of the sample space, which is 1, equals the probability of the union of the sample space with the empty event, which equals the probability of the union space plus the probability of the empty event, which is just again 1 plus 0. Also, since the probability of the entire sample space equals 1, we know that P of A is less or equal than 1 for any event A. Something you should consider is that there's a difference between discrete probability models and continuous models. Let's get back to the coin toss example so we can discuss discrete models. Consider again an experiment involving a single coin toss, so there are only 2 possible outcomes, which are heads and tails. So the sample space is the set of head and tails. The events, as we said earlier, are the subsets of the sample space, so heads and tails, only heads, only tails, or the empty event. If the coin is fair, and that is a very big if, we can assign equal probabilities to the 2 possible outcomes and say that the probability of heads equals the probability of tails, which is 0.5. So the probability of the entire sample space, which is heads or tails, equals 1, which equals the probability of heads plus the probability of tails, which is 0.5 plus 0.5. And of course, the probability of the empty event, which is neither heads or tails, is 0. This will never happen. What about our dice toss event? What is the probability of A here? The same reasoning applies. If the dice are fair, then the 36 possible outcomes are equally likely. So we can assume that each possible outcome has the same probability of 1 over 36. Using the additivity axiom, the probability of A is the sum of the probabilities of its elements, which are 6 elements. Each one of them, as we said, has a probability of 1 over 36. So the probability of A is 6 times 1 over 36, which is 1 over 6. We can generalize that reasoning through the discrete uniform probability law, which tells us that if the sample space consists of n possible outcomes which are equally likely, then the probability of any event A is given by P of A equals number of elements of A over n. So if single outcomes are equally likely, we can just divide the number of elements of our event by the total number of outcomes in the sample space. Now let's briefly discuss continuous models. If we try to use the same reasoning we used for discrete models here, we are going to run into a problem. Imagine throwing a dart at a square dartboard. The sample space omega is all the points inside the square. Suppose the dart lands uniformly at random. Now, what is the probability that the dart hits exactly the point 0.5, 0.5? If that probability were positive, then every other point in the square would also need a positive probability. But remember, the square has infinitely many points. The total probability would add up to infinity, which is impossible since the probability of the entire sample space needs to be 1. Therefore, the probability of hitting exactly one single point must be 0. So the probability of the single event hitting the point 0.5, 0.5 is 0. This may sound counterintuitive, but one way of thinking about it is thinking of probability as areas. What is the area of a single point like this one here? It's 0, right? But that doesn't mean that adding up all points won't give you the whole area. It will. It's just that it doesn't make sense for us to talk of single points as areas, the same way that it doesn't make sense for us to talk as single points or single outcomes in continuous models probability. In examples like this one, it makes sense to talk of intervals. So we could say that the dartboard is a unit square, and therefore the sample space, the entire sample space, is an interval from 0 to 1 by an interval from 0 to 1, which is what we see here, right? And then we can make questions in terms of area. For example, consider an event A, which is the dart hits the left half of the board. That's the region from 0 to 0.5 and from 0 to 1. So this entire area. Let's write it down. The dart hits the left half of the board. What is the probability of A? It is the area of the event divided by the area of the entire sample space, which in this case is easy to see that it's 1 over 2.